All right, so this is the second video from chapter 10. We're going to cover, I believe, most of section 10.3. All right, so the first two panels are going to be just sort of justifying that example we did previously and using instead of permutation test to calculate a p-value, we're going to use an actual distribution, which is going to lead to some issues that we'll then resolve, okay? So this is the chi-square test of independence using the chi-square distribution. So in the early 1900s, it was observed that the chi-square test statistic, which we calculated last time with that death penalty example, under the null hypothesis, so assuming that the two categorical variables are independent of each other, which for us was education level and favoring or opposing death penalty, under the null hypothesis, it was observed that that test statistic followed a certain distribution called the chi-square distribution, which is hence how they then named the test statistic chi-square test statistic, with I minus 1 times j minus 1 degrees of freedom. I was the number of subcategories in the first categorical variable. So in the education, I would have been 5, the 5 education levels, and j is the number of subcategories in the second categorical variable. So for the death penalty, it would have been 2, opposing, not opposing, or favoring and opposing the death penalty. Okay. So here's the PDF of the chi-square distribution. M is the degrees of freedom, and this gamma, that's sort of a generalization of factorial function, and it can be applied to decimals as well. So it generalizes factorials. You do not need to have that thing memorized. But it's a continuous distribution, and that continuity is going to lead us to make corrections in a special case coming up. Okay, so in the early 1900s, they also realized that the chi-square test statistic wasn't really following the chi-square distribution unless the expected counts, so that was in the red writing of the table before, and if the expected counts in each row of the contingency table was good enough, was large enough, okay? Where the I minus 1 times j minus 1 degrees of freedom comes in is if I fill in the first I minus 1 rows and j minus 1 columns of the contingency table, the remaining entries I get for free since I know the row totals and the column totals. So it's sort of like that's unnecessary information, so I don't truly need it. So I do truly need I minus 1 times j minus 1 pieces of information for that contingency table. I need that many cells of information. The rest I can then figure out, okay? So in our example, I minus 1 times j minus 1 would have been 5 minus 1 for educational levels, 2 minus 1 for favor opposed. So our chi-square distribution would have 4 degrees of freedom, okay? And if I'm going to calculate the p-value, I'm going to use the CDF of the chi-square distribution. So now I'm going to calculate the p-value via a distribution, okay? So the R code is quite simple. This p chi-square x comma m, that's the R code that tells me the probability that my distribution is less than or equal to my observed C value, okay? So for our death penalty example, I would have used to get the actual p-value, I need the probability that it's greater than our observed C value. So I'm going to do 1 minus p chi-square. 23.45 was my observed C value. 4 is my degrees of freedom, and that cranked out to 0.001029. Okay. Boy, the lighting gets all funky on this thing, doesn't it? All right. Well, hopefully you can stop the pause, make sure you got everything down, and I'll wheel us on over to the next one. Gotta do some furniture rearranging. Where am I going? Go like that. Okay. So I'd pause it and copy this down. Notation's pretty picky here, so just be careful with the dots and everything else, and we'll go through this. Okay, so this is more formally how we're approaching this chi-square distribution approach, okay? I've got categorical variable A and B. One is the response variable, so favoring or opposing. One is the input variable, education level. I've got total number of data was N. For that example we did, it was 1,307. Capital N sub ij, that's going to be a random variable of the number classified by the ith level of A and the jth level of B. So that's the random variable of the number of people in one row column, one cell in our contingency table. Our observed value of capital N sub ij is denoted lowercase n sub I, comma j. So those are the entries we had in black in our contingency table about death penalty and education. Okay, now Pi sub I, comma j denotes the probability that a randomly selected individual is going to be classified by that ith level of A and the jth level of B. So it's the probability that one of these random 1,307 people is going to be in a specific ith row and jth column. So it's a specific education level and a specific opinion on the death penalty. Okay. All right. Now, the expected value of the number of people who should appear in that cell is going to be the total population times the probability of appearing in that cell, which makes sense. More notation, R sub I is going to be the total number of people in row I. So I'm just going to add up the random variables for each cell from column 1 through 7 in the ith row. C sub j is going to be the column total for the jth column. So I'm going to add up the random variable for the number of people in rows I equals 1 through capital I in column J. Pi dot is going to be the sum of the probabilities in the ith row. P dot j is going to be the sum of the probabilities in the jth column. So these are what we'd call the marginal probabilities from Math 313, right? Okay, and now we're testing independence. That's what we're trying to do here. So our null hypothesis is going to be that the probability of belonging to the ith row and the jth column, that particular cell, is going to be the product of the probability you belong to the ith row and the jth column, okay? That's what independence would mean, okay? But the product of those two probabilities gets you into that cell. And that has to be true for every single cell, from I equal 1 to capital I and j equals 1 to capital J. Alternate hypothesis is that the probability fails to be the product of the row probability and the column probability for some I and j, okay? All right, now our test statistic is going to be that C value again that we had before. And we believe that it approximately follows this chi-squared distribution with I minus 1 times j minus 1 degrees of freedom, okay? All right, well, Pi dot and P dot j are not known, so we're going to use estimators. So the probability when the ith row is going to be the total number of people in row I divided by the total number of people that we have in our sample, that 1307. And similarly for an estimator of the jth column probability. In which case, the expected number of people in that ith row jth column, that cell is going to be our total population times the probability being the ith row, probability being the jth column. And if I throw in my estimators and simplify, I get RICJ over N, okay? And I can then calculate my chi-square test statistic. There's the number of people I observe in the ith row jth column minus the expected squared divided by expected, and that expected came from the row above it. And we believe this statistic approximately follows a chi-square distribution with I minus 1 minus 1 degrees of freedom. It works really well if each n sub ij is large enough. Else we should probably use a permutation test, okay? All right, so get that copy down. We'll shimmy on over to the next one. Okay, So, so one more here. Cool. Okay. So the previous panel that we just looked at, that was sort of the theoretical, and the R code for that can happily be accomplished. I didn't show you the R code for the very first panel of this video, but I wrote out the exact command, and I can show you at the end of this video when I pop over to R for another purpose. Okay, so we've got this chi-square distribution, and R can tell us a p-value based on that. We're going to look at one special case, and we're going to figure out how to work with this special case in two different ways. Okay, so the special case is when our two categorical variables each have two subpopulations. Okay, so we're looking at cases when I is equal to 2 and j is equal to 2. And we've got two methods for dealing with this special case. One is to make a continuity correction, and that's because our chi-square distribution is a continuous continuous distribution. And when we have so few categories, that creates problems, but we can do a quick correction. The other way is to do more of an exact test, which used to be incredibly laborious, but now with R, we can do it rather quickly. Okay, and we'll run through this example right here with both the Yates continuity correction and Fisher's exact test. Okay, so again, in black is the data we gather, and in red is then things that I'm computing after I gather data. So here's our categorical variable. I've interviewed, I think, 209 people, and I've classified them as either short or not short. Okay, so that's the input variable, two subpopulations. And then I'm looking for a response variable of whether they were bullied or not bullied. Okay, so I got short, not short, bullied, not bullied, and I put my people, all 209 people, into one of those 4 cells. I then added up the rows, added up the columns, got my total. And what I observe is that overall, 72 of the 209 people I interviewed were bullied. Okay, so that's a bully rate of 34.4%. All right, now once I've got that expected percentage of people being bullied, I can figure out, the overall percentage of people being bullied, I can figure out how many people I would have expected to be bullied in each of these rows if it was independent. Because remember, if being bullied is independent of being short or not short, then I should expect each row would approximately have 34.4% of the people being bullied, the short row and the not short row. Okay, so if 34.4% of people should be bullied, the expected number of bullied in the short row would be 0.344 times 92, which is 31.7. And in the not short row would be 0.344 times 117, which is 40.3. And then the expected not bullied is the rest, basically. So 60.3 and 76.7. Okay. All right. Now, my null hypothesis is that being bullied is independent of height. So they are independent. So the expected values is what I should expect. Okay. The alternate hypothesis is that being bullied is not independent of height. All right, so make sure you got that table down, and then we'll move on to the Yates continuity correction. Okay. So maybe I'll just get this one a bit closer for you. Pause and copy that stuff down. Maybe you can still read it way over here. Okay. So in this I equals 2, j equals 2 situation, we can slightly revise our chi-square statistic with a continuity correction. So my new C value via Yates is going to be take the observed minus the expected in absolute value for each cell, subtract 0.5, square it, divide by the expected, sum all that stuff up. Okay. All right. Well, if I do this contingency table over here without the continuity correction, I'm taking my observed minus expected squared over expected from all 4 cells, adding it together and getting 9.14. And then I'm asking R to give me 1 minus the P, the CDF of the chi-square distribution at 9.14 with 1 degree of freedom. 2 minus 1 for I minus 1, 2 minus 1 for J minus 1, so 1 times 1. And I get a p-value of 0.0025, which tells me to reject the null hypothesis. Okay? Now, with the Yates continuity correction, I'm going to take observed minus expected and absolute value, subtract 0.5, square the result, divide by expected, do the same for the other 3 cells, and I get a test statistic of 8.26. Run it through the exact same R code with 1 degree of freedom for the chi-square distribution, and I get 0.004 for my p-value. Okay. Now, please note, in both of these cases, right here is where I'm using the distribution, the continuous chi-square distribution, where R is. Okay. So we're using a distribution to calculate our p-values here, not a permutation test like we did earlier, strict distribution. Okay. All right, well, with the Yates continuity correction, we get a more accurate p-value, 0.004, which is telling us that there's no way we should believe that these two things are independent, right? All right, so there's statistically significant evidence to reject H0 and conclude that being bullied is not independent of height. So in other words, height has something to do with it, okay? All right, one more panel for this video. Oops, bring that over. Okay. All right. So then the other way we can go about sort of figuring out something pretty exactly in this case where I equals 2 and J equals 2, it's called the Fisher's exact test. And again, I'm going to calculate the p-value the way I always do through in general. I want to calculate the probability of finding an outcome C value as extreme or more extreme than the one observed, but this time I'm going to use the hypergeometric distribution. Okay. Now, for the Fisher exact test, I need to make an assumption. I need to assume the row and column totals are fixed. So knowing the row totals and the column totals and the very first entry, the 1-1 entry of the contingency table, determines everything else in the contingency table. Because remember, it's only a 2x2. So what I'm saying is, if I knew the number 42 were short and bullied, that 1-1 entry, and I know my column totals and my row totals, like basically by magic square type thing, I can figure out these other 3 entries. Okay, so that's the only thing I really need to worry about. So in general, the setup is I've got subcategory A and B, short, not short. Subcategory C and D for the response variable, bullied, not bullied. I've got entries A, B, C, D, row totals A plus B, C plus D, column totals A plus C, B plus D, and totals of A plus B plus C plus D. What I'm going to do is I'm going to say, let's let X be that count in 1-1, so 42 in our case. And via the hypergeometric, we're going to calculate the probability of that first column, right? So that probability is of the 92 short people, pick 42 of them to belong in that category. And of the 72 bullied people, pick 30 of them to belong in the 1-2 entry. Sorry, 2-1 entry. Okay. And then divide by 209, 272. Okay. So we're going to calculate that hypergeometric value, or in general, of the A plus B people, pick A of them. Of the A plus C people, pick C of them, and divide by the total population, choose A plus C. So that's the hypergeometric distribution. Okay. All right. Once I calculate that, the way I'm going to get my p-value is the p-value is going to be 2 times the minimum of the probability that X is greater than or equal to 42 and the probability that X is less than or equal to 42. So as extreme or more extreme. So 2 times the minimum of those 2 values. And if I do this via R, which I'll show you in a minute, you get a p-value of 0.0033. Okay. Now we can use this Fisher test when the row and column totals aren't fixed, okay? And that's called conditioning. And that's when we compute the p-values on the information on the actual value of the sample size. And we've actually done this frequently. I'm not going to say this is vital, but if you read section 10.3.4, you can get a bit more information on that. Okay. All right. So at this stage, we're going to switch over to R, and I'm going to show you this computation, and I'll show you the computations from the previous panels. But hopefully that was pretty clear. Okay, so here we are. And our studio. Okay. So here's the example we started this video with. So here's the Yates continuity correction example. All right. So without the continuity correction, we got a C value of 9.14, and I can get the P value of it at 0.0025. Now, if I want to do the Yates continuity correction, what I'm first going to do is I'm going to basically set the rows. So the first row was 42, 50. The second row is 30, 87. Okay, so I'm going to set those rows and call that matrix for map. And then I'm going to do the chi-square test on map. And that automatically does the Yates continuity correction, as you see in the output. Pearson chi-square test with Yates continuity correction. And I get a p-value of 0.004, as I have on the board. Right now, if I want to do the Fisher test, my first command is exactly the same. I'm going to fix the matrix. First row is 4250, second row is 3087, and then I'm going to ask it to perform the Fisher test of that matrix. And I get a p-value of 0.0033. Okay. All right, so we got a variety of p-value tests, but they're all significantly less than 0.005. And the Yates continuity correction is pretty close to the Fisher exact test. Fisher exact test would be the true p-value that we should use. All right, this concludes our second video.